Now we'll begin to study vector spaces, and to start, let's just create the definition of vector space and consider a canonical example. A vector space over a field F, refer back to the previous videos to understand what a field is defined to be a set V on which there are two operations: addition, which associates to any two vectors, v1, v2 within V, an element v1 plus v2 in V, and scalar multiplication, which associates to any pair of scalars or elements of the field A and F, and a vector v in V, an element AV which is in V. That is, V must be an abelian group under addition. Scalar multiplication will be associative in the sense that AB times the vector V is equal to A times the vector B times V for any A, B in F and V in V. We have that the multiplicative identity 1 in F must be the identity for scalar multiplication, that 1V is equal to V for all V in V, and that the distributive law holds for addition and scalar multiplication. A times V1 plus V2 is equal to A V1 plus A V2, and it distributes the other way. A1 plus A2 times V is equal to A1V plus A2V for all A, A1, A2 in F, and V, V1, V2 in V. Note the definition of a vector space involves both the set V and a particular field F. The elements of V are called vectors and will be denoted usually with bold-faced letters, but when written you can write an arrow above them, and the elements of the field are called the scalars in this context. If 0 in F is the additive identity element in the field, and for any vector V, then we have that 0V is equal to 0 plus 0V is equal to 0V plus 0V. So since V is a group under addition, it follows that 0V must be the identity element of the group, and this element is denoted by 0 within V, and it's called the 0 vector. That is, for any vector V, multiplying it by 0 will give you the 0 vector. The simplest vector space over any field F is the trivial vector space, consisting of just the 0 vector alone. But a more standard example of a vector space over a field F is the set F to the n, consisting of all n tuples of elements in the field F. We will view that a vector within F to the n is a column vector written V is equal to x1 all the way to xn, where xi are the coordinates of the vector V and are scalars within the field. We can associate to any vector its transpose, which is the row vector, x1 up to xn, written from left to right. This alternative version of vector plays a significant role other than just for notational convenience, for instance in matrix multiplication. Sometimes for convenience, though, we will write a vector by listing out its coordinates, although you still view the vector as a column vector. To understand how the sum operation in the vector space will operate in the case of f to the n, we note that we sum two vectors by summing together the coordinates of the vectors element-wise. And then we perform scalar multiplication by scaling each of the coordinates by whatever scalar you choose. That is, for a vector x consisting of elements x1 to xn, and a vector y consisting of coordinates y1 to yn, we write their sum x plus y as the vector which has coordinates x1 plus y1 all the way to xn plus yn. And then for scalar multiplication, we have that a times x1 to xn is equal to ax1 all the way up to axn for f in A. You can check that these definitions will satisfy our axioms for a vector space over a field F, so we see that f to the n is a vector space over the field F. With that quick video out of the way, thank you for watching, and next time we'll continue by considering subspaces.